We're going to discuss chemical bonds, and the two that we're going to focus on right now are ionic bonds and covalent bonds. Now, what is a chemical bond? A chemical bond is the attractive force that holds a group of atoms together and makes them function as a whole unit. So for you to have a bond, you have to have multiple atoms. And we're going to look at how the atoms are connected to each other and what holds that whole bond together, because each one of these has a different way of being held together. Now, bond energy is a calculated form of energy that we can use to determine how strong a bond is. So bond energy is the energy required to break a bond, and we can use that to determine different types of properties as we learn more about chemical bonds. The first one we're going to focus on is ionic bonding, and an ionic bond is when a salt is formed, and again, a salt is truly just an ionic compound. And to remind you, an ionic compound is a metal and a nonmetal, always a metal joining with a nonmetal. And what happens as we have electrons, one or more, usually up to 3, they are being transferred. So it's actually being taken from the metal and the nonmetal is accepting it. And so when the metal loses an electron, it becomes a cation. It has a positive charge here. And then the nonmetal becomes an anion, which means it gains the electrons. Okay, now what holds this ionic bond together is called electrostatic attraction. Electrostatic attraction, which is basically just a fancy way of saying that their opposite charges are holding them together, just like a magnet is held together, positive and negative. Now, the other type of bonding we're going to look at is covalent bonding, and this is different because it is sharing. So the big difference here, we're looking at sharing versus ionic bonding being a transfer. So it is the sharing of valence electrons between two nonmetals. And we're going to then kind of subcategorize into nonpolar covalent and polar covalent. But let's again just refer to this picture to help us kind of understand the difference. So if you think back to the previous ionic bond, you could see that the atoms were transferring electrons, but they're just kind of held together because of the positive and the negatives. Now, the covalent bond is held together because they are physically sharing either 1, 2, it could be 3 or 4 electrons between the two of them. So remember, the whole goal of a bond is to create 8 valence electrons. So what they do is they have their own, but then they are missing 1, 2, or 3, or even 4 to get that octet in their valence shell. So they bond with something else that has a similar amount that's missing, and then they both can count this as their own to fulfill their octet. And so we can see that again, they come together and they are connected via a sharing. Now we're going to go ahead and discuss the difference between nonpolar and polar in terms of covalent bonding. There is no such thing of polar or nonpolar ionic, just covalent. So nonpolar covalent is when we have a covalent bond, again, that's sharing of electrons, and they're being shared equally. That means, and you can see that right here, they're basically perfectly in the middle between the two atoms. No one is pulling more than the other. Nonpolar, no one is pulling more than the other. Okay, so it's like playing tug of war and you had twins on either side that have the same level of strength. And so that knot in the middle does not move. They both are sharing equally. Now, what's a lot more common here is polar covalent. Polar means someone is pooling more than the other. Polar pooling. So it is a covalent bond when electrons are shared unequally. And you can see that here over on the right side. And you can see that these electrons, although they're being shared, they are a lot closer to the B atom than they are to the A. So this is, because it's not equal, it is polar. Okay, polar covalent. So it's still being shared, it's just unequally. And so this, therefore, results in a separation of that positive and negative charge. But it's not a full transfer of electron like an ionic bond. It's called a partial transfer. So we're going to go ahead and kind of define what these mean and where to put them. But just quickly to give you an overview, the one that has the electrons being pulled closer, the stronger pull, gets this partial negative sign. And that is because electrons are negative, so it's getting more of the negative strength of those electrons. Where the other atom that is still sharing but doesn't have the electrons as close gets a partial positive sign. And again, this just stands for partial positive, partial negative in terms of polar covalent bonds. You do not use partial positive, partial negative in terms of nonpolar, only polar. And I like this picture because it kind of demonstrates the three different types, or the two bond types, and then the subcategories. So on the left side here, we have non-polar covalent, and you can see two Cl molecules equally sharing. Okay, so equally sharing those electrons, so they both have an octet. Now in the middle, we have polar covalent, and you can see here that the picture doesn't demonstrate it very well, but the picture is colored. And so the side that is blue, or the right side, and this arrow is really demonstrating that the chlorine is hogging the electrons or pulling them tighter. So it's like playing a tug of war and having like a 10th grader and having like a second grader, right? That's probably too much of a drastic difference. Let's say like a 6th grader and an 8th grader, okay? So that 8th grader, is pulling and probably has that knot closer to their side, but the 6th grader is still holding their own. So that's kind of how you have to think about it. So the chlorine, because it's holding it tighter, pulling it more towards its side, gets this partial negative, and the hydrogen is a partial positive because it's kind of giving it up a little bit, but it's still sharing. Now, when the thing that it is sharing with, that it theoretically would be sharing with, is even stronger, it then becomes a complete transfer. Okay, so instead the electron of being shared, it actually is stolen, taken away, and so we see that instead of it being a partial positive, partial negative, we have a positive and a negative overall. Okay, and so we have full ions being created here. Now, we can make educated guesses of how kind of strong an atom is in regards to pulling the electrons when they're being shared, but we actually have a chart that we can utilize to help us figure out, the strength of the atoms in terms of sharing and the pull that they have. So that is called electronegativity. And electronegativity is the ability of an atom to attract shared electrons. So this is some sort of covalent bond. So the greater the electronegativity, the more pull on the shared electrons. And therefore, when you have more pull, they're being shared unequally, and the one that's pulling harder gets the partial negative. The one that is kind of giving it up a little bit is a partial positive. And you can see here, I kind of filled these in, but these are the electrons being shared, and they are closer to the partial negative. Now, the atom that has the smaller actual, numerical value of electronegativity, we're going to actually look at this on the next page, will become the partial positive, and the one with the higher value will become the partial negative. So let's go ahead and practice that. So you will always be given this chart. You just have to know how to utilize it. So again, let's kind of pick the most electronegative atom on this entire periodic table. So the atom that, if you're sharing with it, would hog the electrons the most. And that is going to be fluorine. Fluorine is the most electronegative atom on the periodic table. It has the highest electronegativity value of 4.0. And so the least is kind of a tie here between the cesium and the francium. So the most fluorine, the least are cesium and francium. Okay, so our trend here is it increases to the right and decreases as it goes down. Now, let me show you how we can utilize those values in that previous chart. We're going to go ahead and look at bonds, shared bonds, so covalent bonds, and these are all polar, and we'll kind of talk about how we know that here in a second. And so what we're going to do is look at the values. So let's go back up, and we have N and F for letter A. So N is 3 and F is 4. So what we're going to do is the one that has the higher value gets the partial negative sign, and the one that has the lower value gets the partial positive. Meaning fluorine is going to have the shared electrons closer to it than the nitrogen would, because it has a tighter pull. So let's go ahead and continue doing these. No matter what, fluorine is going to have the negative, so that's kind of an easy one. And then let's check out S and Cl. I'm just going across here. S and Cl, so 2.5 and a 3. So the Cl is going to hold the electrons more, or pull them. Now, Cl-Cl, this would be an example of a non-polar bond because they're the exact same. So therefore, we do not use partial positive and partial negative. We only use partial positive and partial negative for polar because something is pulling more than the other. So let's look at N and O for letter D. N and O. Okay, O is going to pull it a little bit more than the N. And then let's look at Si and F. Now, F for sure is going to be the higher one there. All right, go ahead and make that a little more squiggly. All right, now, I like this picture also. It again demonstrates the sharing of the electrons. So I'm kind of, talking about the same concept because it is so important in this chapter. And the polarity of a bond depends on the difference in the strength or the electronegativity of the atoms that are sharing the electrons. So again, this would be a nonpolar bond, nonpolar covalent because it's being shared. This would be a polar covalent bond because you can see that they're still sharing here. They have a connection of their electron clouds, but it is the electronegative one to the right is probably pulling it more. And then you can see still a separation here. Remember what holds these together in a bond is that electrostatic attraction, that positive and negative attraction. Whereas covalent bonds, they're literally stuck together because they are sharing something. So let's go ahead and look at these three types of atoms. And the way to do this is actually very simple. We're going to have to kind of go back and forth on that chart. So let's go ahead and look at A, L, and O on the chart. And I'm going to do the first one with you, and then you can go ahead and fill in the rest of the numbers as we practice this. So I'm going to go ahead and look at the AL and the O here. So AL is 1.5 and the O is 3.5. And of course, you would be provided with this chart. So the AL we said is 1.5 and the O is 3.5. Okay, and so the type of bond here, we are going to be given a chart to do this, but basically if you have a 0 difference to a 0.4 difference, it's non-polar covalent, and I will show you how to do this. If you have a 0.5 to about a 2 point, I think it's 3, but I will give you this chart as well. That would be a polar covalent bond. And if it's between a 2.3 to a 4.0, it would be an ionic bond. So we're going to go ahead and utilize those differences. Now, the way to do this is you literally just take the two values and you subtract them, okay? So 3.5 minus 1.5 gets us 2.0 here. And so the type of bond is going to be, when we utilize our chart down at the bottom, is going to be polar covalent. And the charges, the O is going to get the partial negative and the AL is going to get the partial positive. And the electron distribution, the O is going to be, having the electrons closer. They're still shared, but they're going to be unequal. Okay, so let's go ahead and you can go ahead and back and look at your chart. I will just provide these numbers for you if you want to use those. So N is 3.0 and O is 3.5. Okay, and so when we subtract these, we get 0.5, and our type of bond with that is also polar covalent. And so we said the O is going to be a little more electronegative, and the AL is going to, he's in the past example again. The N is going to be the partial positive here, and they're going to still be sharing. And so therefore it is going to be shared electrons, but it is going to be unequal as well. And then we're going to go ahead and look at this last one, O and O. Now here's a hint. When it's the same atom, the exact same atom twice, when you subtract them, it's going to be 0 no matter what. So therefore, this is a non-polar covalent. And so there's going to just be an O, and there's going to be equal sharing. No overall charges. Okay? All right, so let's focus ourselves a little bit more on ionic bonding. We just did covalent bonding. An ionic bond is a chemical bond formed by that electrostatic attraction, and that's a term I said to you a little bit earlier in this video. And again, that's just a fancy way for saying the positive is attracted to the negative. So the positive part of the metal, when it loses an electron, is attracted to the negative of the nonmetal when it gains one or more electrons. So again, the big term here being transferred. One or more valence electrons are transferred from the valence shell of one to the valence shell of another. Remember that one is a metal and it's going to a nonmetal, typically. And you can see that here. We had atom 1 with 1 valence. We had atom 2 at the bottom here with 7 valence. So A is now in a previous valence shell, and it's fulfilled. It has an overall positive charge because it lost an electron. It has one more proton. And then we can see here the nonmetal gaining that electrons, having an overall negative charge. And what holds this together, this ionic molecule, is electrostatic attraction. And again, now both of them have an octet fulfilled or satisfying their octet, so therefore they are happy. I like this picture also because it really shows you that the transfer of electrons for this is actually, it's literally being taken from one. So we have sodium here with 1 valence, chlorine with 7 valence. Sodium gives it up, and then its now valence shell is this one. So I like that picture to kind of show you that it also is happy because it has an overall valence shell of 8 below it. And again, the metal loses an electron. It becomes a cation. That should be a little plus sign. And the, I'm not sure, this would just be Na, and this would just be Cl, just neutral. And then Na would lose an electron, become a cation, because it has 1 more proton. And then Cl would become an anion because it gained 1 or more electrons and has a negative charge overall. So these are considered atoms before, and then these are considered ions after because they've gained or lost an electron. Now, the term isoelectronic refers to different species, which is just another fancy way of saying atoms, having the same number and electron configuration as each other. So if you were to look on a periodic table, and hopefully you have one near you, if you look at neon's electron configuration would be very similar, actually the same as sodium with a +1 atom, or excuse me, a +1 charge, because sodium loses an electron. And when it loses an electron, the electrons that it has matches the number that neon has. And then same for fluorine. Fluorine that has gained an electron has the same number of total electrons as neon. So if you were to count the electrons up, and they were all the same, and they looked at all the same as a noble gas that they're close to, that is called an isoelectronic series. So how could you tell if something is isoelectronic with other things? You'd write the electron configuration, or you'd count the electrons and see if they are the same and they match the noble gas that they are near. So let's practice that here. So we have chlorine -1 and we have calcium +2. And we're going to go ahead and write our electron configuration for that. Okay, so remember what electron configuration is 1s2, 2s2. Let me find my own periodic table here. 2p6, 3s2, 3p5. And I'm working from memory here, so hopefully that is correct. But the issue you have to keep in mind is that because you have a -1, so this is chlorine that I just showed you, but because you have a -1, you need to add 1 extra electron. So we're going to, instead of making this a 3p5, it's now going to be 3p6, okay? Because chlorine has a total of 18 electrons because it gained 1. Oh goodness, I said 6 and wrote 3. Who knows what I'm doing here? All right. So write the normal electron configuration, and then you can adjust according to how many are gained or lost. So I'm going to go ahead and do calcium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now that is just normal calcium, but I want to do calcium +2, and you always lose from the valence shell. So your valence shell is going to be this last one. So I'm actually just going to get rid of that. And so therefore, these are the electron configuration for ions. I think this is the first time we're seeing this, and we'll go ahead and do a little bit more practice in class. Now, are these isoelectronic? Yes. What do they both have an electron configuration similar to? They're both similar to argon, okay, because they have noble gas electron configurations, meaning they have a fulfilled octet shell. Now, let's go ahead and talk about when we have transition metals becoming ions. So let's write the electron configuration for just iron in general, okay? I'm going to go ahead and just write iron, the atom. 1s2, 2s2, 2p6. I'm going to go ahead and 1, 2, 3, 4, 5, 6. Okay, so this is just iron atom. Now, this is a new concept for you. Iron +2 is going to lose 2 valence. And you have to keep in mind, what is my valence shell in this iron electron configuration? Right here. It's not the last. It's the one with the highest number, the highest energy level, or the highest energy shell. That is the 4. So when it loses 2 electrons, it's actually going to lose that whole shell. Okay, or that orbital is probably a better term, but also that shell. So when I write the electron configuration for Fe plus 2, I just am going to write everything, but get rid of, or not even put, the 4s. 3p6, 3d6. So I know it's a little bit odd, but this is how you do electron configuration for transition metal or d-level orbital atoms. Okay, you remove the highest energy, which is always going to be that s. Now, Fe plus 3 is still going to lose this as well, but it's also then going to lose one of these, okay? So this now becomes 1s2, 2, excuse me, that's a 2p6, 3s2, 3p6, I'm writing too fast here, 3d5, okay? So after it removes the valence electrons from that s shell and you need to remove some more, you then continue to remove from that d. Now, I will let you know, you are not going to be able to look at, for example, if I just gave you this and not what atom it was, you could not figure out what atom it was for a transition metal. So keep in mind that this is really only a one-way thing. I'm not going to give you this and ask you what ion it is because you don't know how many you've removed. Okay, if it was Fe plus 4, you'd remove more D. So it's just you being able to look at an ion